Hello friends, welcome to YouTube channel Tech Guru Gautam Prasad. Analog type ammeter and voltmeter and galvanometer as well. We are going to discuss in this video. So let's proceed. Analog type ammeter and voltmeter. Introduction. Both the types of instruments work by a deflecting torque produced by an electric current which moves a pointer across a calibrated scale. As you can show, a voltmeter and an ammeter has been shown in the picture, and you have a calibration from 0 volt to 300 volt. Up to 300 volt, this meter can measure, and here from 0 to 30 amperes. So every uh, meter has got a scale calibrated, and this is calibrated from minimum to maximum value the instrument can measure. So here this is calibrated. Calibration means it is, the pointer is set in such a manner that it reads correctly the values on the scale. Let's proceed. So analog ammeters. These meters measure electrical current by connecting them in series within the circuit and requires low internal resistance to avoid disturbance to the current being measured. So as you can see here, there is a simple electrical circuit where this ammeter has been connected in series with the load to measure the current flowing through the circuit. This arrangement tells us that majority of the current is bypassed to the load, and the meter itself is consuming very less amount of the current to deflect the pointer of the instrument only. So that is the purpose of measurement. The deflection, lets us read the value of the current flowing in the circuit. So that is it. Now let's proceed to analog voltmeters. So analog voltmeters measure the electrical potential difference, which is also termed as voltage, between 2 points by being connected in parallel with these 2 points and need high internal resistance. Contrary to the earlier situation, this needs high internal resistance to prevent current from flowing through them. So here the situation is different. So as the voltmeter has been connected to measure the potential difference between these 2 points across this resistance, while doing so, majority of the current again is not passing through this instrument, whereas only a small amount of the current passes through this instrument, and in order to ensure that so that this instrument is not damaged by the current, we are connecting high resistance in series with this instrument so that only a meager amount of the current flows through the instrument, and that causes the deflection of the pointer in order to measure the voltage. So that is how this instrument operates. So as you can see here, the connection of the voltmeter is done parallel to the 2 points across which this voltage has to be, or the potential has to be measured. Analog ammeter basics. So resistance, as we have already discussed this point, has a low internal resistance so that it does not significantly affect the current in the circuit. So, majority of the current, is bypassed to the load, and that ensures that instrument is consuming only a partial amount of the current, very less amount of the current, just to cause the deflection of the pointer. The construction often built by adding a low resistance, that means low resistance is connected in parallel to the instrument, so that uh, the majority of the current is bypassed and does not rush into the ammeter parallel with the galvanometer. So basically, we will discuss how the galvanometer can be converted into an ammeter. But for this place, only we should understand that a shunt resistor is connected across a galvanometer in parallel with the galvanometer to measure the current. So the operation, the current flowing through the coil creates a magnetic field which causes the movable iron piece. This is talking about the movable iron, moving iron instruments. So there is a movable iron piece or the coil to deflect the pointer on a scale. So either the movable iron piece or the coil, because of the flowing current, causes the deflection of the pointer on the scale, and that is how it measures the ammeter measures the current. In the similar fashion, analog voltmeter basics also has the similar explanation, but the only difference is that it has high internal resistance to draw minimal current and thus has a negligible effect on the circuit's voltage. The construction built by adding high resistance multipliers resistor, high resistance multiplier resistor in series with the galvanometer, and the operation is like this. A current proportional to the voltage is passed through the a current. Basically, the current is the only thing that can cause the deflection of the pointer. So that is why current is made to pass through the instrument. So a current proportional to the voltage is passed through the meter, creating magnetic field, and that deflects the pointer across a calibrated scale. That is how this instrument operates, the analog voltmeter. Now let's compare these two meters on different fronts. The measured quantity in the case of analog ammeter is electric current, and which is of course measured in amperes. And in the case of analog voltmeters, it is potential difference that is measured in volts. Circuit connection is done in series with the components in the case of ammeter, and analog voltmeter is placed in parallel across the components. Internal resistance of the instrument is very low, ideally zero, in the case of analog ammeter, and in the case of analog voltmeter, this resistance, internal resistance, is very high, ideally infinite. So for the ideal instrument or ideal voltmeter, it will be infinite resistance. For the ideal ammeter, it will be zero resistance. But practically, some resistance is always there. It is not ideally zero. It is not zero practically, and it is not uh, infinite practically in the case of the voltmeter. The circuit effect adds very little resistance, causing a small voltage drop in the case of the ammeter. And in the case of the analog voltmeter, draws very little current, causing minimal disruption. Uh, DC conversion, a low resistance shunt, uh, uh, a low resistance shunt is placed in parallel with the galvanometer, and a high resistance multiplier is placed in series with the galvanometer in the case of the voltmeter. So those are the difference between analog voltmeter and ammeter. So here I have tried to show you the constructional details of the galvanometer. So galvanometer is an instrument that can be converted either into voltmeter or ammeter or any other kind of the meters. So basically this provides the deflection system, and the measurement is done for the current or the voltmeter uh, uh, by this deflection showing, and the calibration is done in a due manner so that it shows ampere or the voltage across the 2 points. So moving coil galvanometer we are going to discuss here. There are different types of the galvanometers, but moving coil galvanometer is very popular in the measuring electrical devices. So it is a device used to detect a small current in electric circuit. That is what is the function of the moving coil galvanometer. Principle: of operation of this galvanometer is that when a current carrying coil is placed in uniform magnetic field, I'm repeating, when a current carrying coil is placed in a uniform magnetic field, it experiences torque, and that torque is given by tau is equal to BINA sine theta, which tends to rotate the coil and produces an angular deflection. So how does it work? B is the flux density, I is the current through the conductor, N is the number of turns, and A is the area. So sine theta is the angle, theta is the angle of deflection, and sine theta is the sine of that angle. So working when current I is passed in the coil, it experiences a torque known as deflecting torque, and this torque is given by BINA, or the radial field theta is 19 degree and tau is BINA. So this magnetic torque tends to rotate the coil. Spring SP provides a counter torque that is also called controlling torque or restraining torque, is known as restoring torque, which balances the magnetic torque and is given by tau is equal to K phi. So, when K, where K is restoring torque per unit twist or torsional constant of the spring. So, this restraining torque or controlling torque is given by the spring used with the spindle. So, that counterbalances the deflecting torque basically. So, that is in equilibrium position, this deflecting torque and counterbalancing torque, that is controlling torque, are equal. When the pointer is not moving after deflection, it is constantly reading a value. Then that condition is called equilibrium, and at that point, controlling torque and deflecting torque are equal. So this implies that BINA is equal to K phi. So I will be equal to K by BNA phi. So this implies that I is directly proportional to phi. I is directly proportional to phi, and hence deflection of the coil is directly proportional to the current flowing in the coil, which can be measured by the linear scale. So, as the current is directly proportional to phi, phi is the deflection. So, this means that we are going to get a linear scale for this instrument. The function of the radial magnetic field, it makes the scale of the galvanometer linear because I is directly proportional to phi. So you are having a uniform scale in this instrument. The production of the radial magnetic field, it can be produced by making the pole pieces of the magnet cylindrical in shape. So you have to take two pole pieces like this, and in the center you have to place the coil, uh, which under the influence of the current will move. So this is the whole thing. Now the third point says necessity of the soft iron core to increase the strength of the magnetic field and hence increase the sensitivity of the galvanometer and to make the field more radial. This core, a soft iron core, is used. So the whole construction in three-dimensional manner has been shown in this picture. As you can see, this is the cylindrical core, soft iron cylindrical core, and on which there is a coil placed, and the pointer has also been fixed on this cylinder, and this is the controlling spring which gives the controlling torque, and this is made basically of the phosphor bronze material, and that is why it is written here phosphor bronze control spring. So uh, uh, the top and the bottom positions have a jewel bearing basically, which makes the entire moving system to move freely on these two pivoted points. We have a lower control spring and we have got a upper control spring. These two are wound in a opposite direction, and these are the pole pieces. These are the pole pieces basically on which is causing the field flux density. So the terminals are to the terminals are here, uh, with the help of which this winding is connected. Okay, the pointer counterbalance. This side of the weight has to be balanced by this side of the weight. That is why some weight is put on the shorter end of the pointer just to counterbalance the weight of this longer part of the pointer. So this is the whole construction of the galvanometer. Let's proceed. Here also, this moving coil galvanometer construction has been shown. This galvanometer is also called sometimes the Arsenal or Western type or the moving coil type galvanometer. So this is popularly known as moving coil type galvanometer, as it was invented by D. R. Sunwell. The Western type, either name it is known as. So, in actuality, if you will see this moving coil galvanometer looks like this. Commercially, it is available in this manner. So, DC moving coil galvanometer, DC voltage is put here. So, the deflection can be caused in either direction. So, zero reads at the center of the scale, and this pointer can deflect left or right, depending on upon the direction of the current flowing through the instrument. So this galvanometer can be converted into ammeter or the voltmeter. Here I have shown you how this galvanometer has been converted into uh, an ammeter. So here is the galvanometer, and low resistance value has been connected in parallel with this galvanometer, so that a large amount of the current is bypassed through the shunt resistor, and very meager amount of the current, very small amount of the current passes through the galvanometer. So this ensures the protection of the galvanometer. At the same time, this current also, the maximum current that flows through the galvanometer causes the full amount of deflection on the scale, uh, deflection of the pointer on the scale. Right. So here also the same thing has been shown, same circuit has been shown. I is the total amount of the current flowing through the load. Ig is the amount of the current flowing through the galvanometer. I minus Ig is the amount of the current flowing through the shunt resistor, and this is basically summing up again to uh, go to the current, go to the load, this value I. So I is the total amount of the current passing through the load. Now the voltage across the shunt resistor will be equal to voltage across the galvanometer resistor. So galvanometer, so considering this condition, Ig into G is the value of the resistance of the galvanometer, is equal to I minus Ig into S. So if we solve this equality, we will get S equal to Ig into G, the galvanometer resistance divided by I minus Ig. So with the help of this equation, you can calculate the value of the shunt resistor, and that will help you in finding the value of the shunt resistor according to the current that you are going to measure. So if suppose your I, the load current, is n times the galvanometer current. So under this situation, what will happen? Your S can be calculated very easily by using this formula. S will be equal to G divided by n minus 1. So suppose your IC is 5 times the galvanometer total load current. So 5 times the total load current. So shunt resistance is going to be the galvanometer resistance. Suppose it is 1 ohm. 1 ohm. So so shunt resistance is going to be G divided by 5 minus 1, that is 4. So, so your shunt resistor will be 1 by 4 ohm. So this is how you can calculate the value of the shunt resistor very easily using this formula as well. So this is also useful. At the same time, this is also useful when the shunt current is given as the number of times of the load current. Sorry, the load current is given as the number of times of the galvanometer current. So that is it. How it is calculated. Shunt resistance is calculated. Here also the same thing has been derived in a different manner, and Ig has been calculated. Basically, the amount of the current that can be handled by the galvanometer. I have taken a numerical example for the calculation of resistances here. A galvanometer has a resistance of 12 milliohm. Current of 150 milliampere produces a full scale deflection of the galvanometer. This is given, and a shunt is connected in parallel with the galvanometer to convert it into an ammeter, and the resistance of the shunt is 70 micro ohm. The resistance of the shunt is given 70 micro ohm. What is the greatest current that the ammeter can measure? Answer, to 1 decimal place. So you have been shown here. It is better to draw a picture with the help of picture. The understanding is better. So you draw a picture and summarize the given values, like Ig 150 milliampere that was given, and also uh, the galvanometer resistance has been given. So the value of the G is given, and the resistance of the shunt is also given. This is 70 micro ohm. So RS and G, the value of these two is given. So you can look at this as this picture has been shown. You can consider it two resistances. This is galvanometric resistance shown as R1, and this is shunt resistance shown as R2. So there is a load current of I plus is flowing through these two resistances and getting diverted, some current towards R1, some current towards R2. So towards R1, let's suppose it is I1, towards R2, let's suppose this current is I2. So if we have to find the current, through the uh, resistor, this shunt resistor I2, then I2 can be calculated as this. Uh, I2 is equal to I plus the total load current multiplied by R1 by R1 plus R2, that is sum of the two resistances. So if we substitute the values in this formula, we will be able to get, the value of I plus. So I plus can be calculated using this. I plus will be equal to I2 into R1 plus R2 divided by R1. So that has been used here. I plus is equal to 0.150 ampere into 0.012 ohm plus 17 to 10 to the power minus 6 ohm and divided by 17 to 10 to the power minus 6. If you calculate, solve this, we will get 25.9 ampere. So this is the maximum amount of the current that it can measure, right? So milli means 10 to the power minus 3 and micro means 10 to the power minus 6, and this must be very much clear when you are solving the problems. Okay, let's. So friends, we have got yet another example of numerical example of this. The current I in the circuit shown in is 2.5 milliampere. This is the circuit. This I, total amount of the current, is 2.5 milliampere, which is the greatest current that can be measured using the circuit as an ammeter. And the resistance of the galvanometer is 10 times the resistance of the shunt. This is given. Resistance of the galvanometer is 10 times the resistance of the shunt. And what is the difference between IS and IZ? Answer, to the nearest microampere. So your I is 2.5 milliampere, that is given. Rg is 10 times the Rs, that is also given. We want to find Is minus Ig. Is minus Ig, the difference. What is the difference between Is and Ig? This is the difference the question is asking. So for that we have to calculate Is and Ig. So I is equal to Ig plus Is, as it is obvious from the picture, and equal to Is is equal to 10 times the Ig. Is is equal to 10 times the Ig, according to this resistance given. So Is is equal to 10 times the Ig. Okay, so if you substitute this value here, you will get I equal to Ig plus 10 Ig, that means 11 Ig. So I becomes 11 Ig. Now Ig becomes I by 11, and Is thus becomes, if you substitute this value here, Is can be calculated, and Is becomes 10 by 11 I. So by having got this, the value of Ig and Is, we can calculate the difference. So 10 I by 11 minus I by 11 will become 9 by 9 I by 11, and as because the value of the I is given, we can substitute this value to get the difference. So 9 by 11, 2.5 milliampere is equal to 2.045 milliampere. That means 2045 microampere. This is the answer. So that is how you can arrive to the conclusion or arrive to the value you have been asked for, as has been explained in the picture. Let's proceed. Conversion of the galvanometer into the voltmeter. This has been shown here. So this is your galvanometer. You have connected a high value of the resistance in series with this galvanometer, so that a very less amount of the current flows through this instrument, and that ensures the safety of the instrument galvanometer as such. And Ig is the amount of the current flowing through this galvanometer in this case, and this is measuring voltage across the 2 points given, A and B. So this is the voltage, B is the voltage across these points. So here also the same thing has been shown. This is the resistor, high value of the resistance connected in series with the galvanometer, to make sure that very less amount of the current flows through the galvanometer to protect it while measuring the voltage in terms of current. So Ig is the total amount of the current passing through this instrument, and so the voltage will be equal to, voltage drop will be equal to Ig into R plus G. R is the high value of the resistance, and G is the galvanometer resistance. So R plus G from this equation becomes V by Ig, and if you want to calculate the value of the R, this is equal to V by Ig minus G. So if this V is N times the galvanometer voltage, suppose the voltage across the galvanometer is N times uh, N times the galvanometer voltage is equal to total voltage being measured, then this N times the Ic into G will become, if you substitute this value of Vg, then this Vg is equal to Ig into G. Ig into G, Ig into G is the total value of the voltage across this galvanometer. And from this, if you want to calculate R, this R will be equal to N minus 1 into G. So this is how you directly, able to find the value of R, the high value of the resistance that has to be connected in series with the galvanometer by using this formula. So suppose mm, your voltage across the galvanometer is uh, 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 V by 10. That means if you multiply galvanometer voltage by 10, you get the total voltage to be measured. So in that case, you have to just make one less than 10, that is 9, and that value has to be multiplied by the galvanometer resistance, and you will find the value of the resistance. So 9G will be the value of the resistance if your galvanometer voltage across the galvanometer is, uh, you know, uh, is 1/10 of the total voltage being measured. So this helps you in finding the values of the high value of the resistance that has to be connected in series with the galvanometer. Here is an example related to the voltmeter. A voltmeter can measure a maximum potential difference of 4 volt and has a resistance of 3000 ohm. When a multiplier of resistor Rm is connected to the voltmeter in series, its measuring range is increased by 12 volt. Calculate the value of Rm. So here the current passing through the galvanometer is equal to, uh, as the voltage is 4 volt and the resistance is 3000 ohm. So Iz can be calculated with the help of this. Iz is equal to 4 volt divided by 3000 volt. So in the similar fashion, if you want to measure 12 volt with the same instrument, the current value of the Iz should not exceed this value. So considering that, a 12 volt can be measured with the same amount of the current passing through the uh, instrument, right? So what will be the value? So considering this is the current, 12 volt will be equal to 4 volt divided by 3000. So if you calculate using this formula, the value of Rm will be equal to 12 multiplied by 3000 divided by 4. So this is equal to 9000 ohm. This will yield a value of 9000 ohm, and that is the value given here. So 9000 ohms is the correct value. That is the value of the multiplier resistance that has to be connected in series with this galvanometer. So another example here, convert a D ensemble movement with an internal resistance of 50 ohm and a full scale deflection of 2 milliampere into a multi-range DC voltmeter with a voltage range of 0 to 10 volt, 0 to 50 volt, 0 to 100 volt, and 0 to 250 volt. So this type of arrangement is there. You are having resistances connected with the help of a selector switch to R1, R2, R3, R4. And these values of different resistances are, uh, you know, making the range of this galvanometer increase from 0 to 10 volt to 0 to 50 volt, 0 to 100 volt, and 0 to 50 volt. So in the case of uh, what are the things given here? Im is equal to 2 milliampere, Rm equal to 50 ohm, and V1 equal to 10 volt, V2 equal to 50 volt, and V uh, 3 is equal to 100 volt, V4 equal to 250 volts. So case 1, S and V RS1 will be equal to V1 by Im minus Rm. So 10 is the full scale deflection divided by 2 milliampere is the current minus 50 is the instrument resistance. So this is the current voltage divided by current, that is resistance, and this value comes up to be 4.95 kilo ohms. Similarly, RS2 is equal to V2 by Im by Rm. So similarly, if you are it is 50 ohms, so 50 divided by 2 2 milliampere, and If you calculate it, it will be 24.95 kilo ohm. So similarly, other values can be calculated, keeping 100 volt, 250 volt, such cases. Okay, so that is how this calculation is done. So thank you very much. Uh, if you like this video, don't forget to give a thumbs up. Uh, if you want to ask any question related to the discussion, you can ask in the comment section. I would like to reply it as early as possible. And if you find this discussion useful for some of your friends, do share it with your friends and the community. And if you are not subscribed to the channel yet, suggest you to subscribe to the channel so that you keep on getting the video updates uh, with the uh, posted videos as quickly as it is posted. Thank you so much once again.